Okay, so we're back here in Lucas's space once again. He's letting us borrow the board. And so remember, we were talking about chapters 8, hypothesis testing. And so to clear up some stuff, we want to make sure we understand all the components of hypothesis testing, talking about specifically the alpha level and the margin of error, and also talking about how to increase statistical power. So remember, we had our 4 steps. State the hypothesis. There's 2. Hypothesis null, no change. Hypothesis alternative, there is a change or a difference. Step 2 is set the criteria. So setting your criteria based on your alpha level, which we're going to talk about a little bit more right now. Your critical region, we're going to get more into that. And then degrees of freedom, we'll do that when we start doing the t-test and other tests. Remember, right now we're talking the one sample Z, like a zebra test. So we're not including degrees of freedom. We're going to run the test, which is, for example, here, our one sample, a Z test, and then, of course, decide significance. And so all this has to do, again, with our significance level. And what is our significance level? Our alpha level. So if we talk our alpha level, I had said the default was 0.05, meaning that we had 95% of the norm, or the body. It means that 95% was inside of the body. So 95% of people in reality all agree or come to some general consensus. So anything that anyone was doing in terms of programming, anxiety levels, you can think of, any type of research being conducted, 95% of the results are all essentially the same. 5% of the results of those samples being used would be significantly different. So that's what we were talking about before. So for example, here, if we talk about the types of tests, we have to clear up a couple of different things. If we talk about using a sample to challenge a population statistic, what are we going to do? We can challenge it in 2 specific ways. We can challenge it in a directional way or a non-directional way. Direction and non-direction lead us to the idea of having tails. In other words, directional is only 1 tail, and non-directional is 2 tails. What do we mean by direction? In reality, direction is basically challenging in a specific area. So are you saying that there is something on the increased side, the higher, the better side, or are you saying something that's going to be on the lower, decreased side, positive or negative? So are you challenging in a particular direction, saying something is better or worse than something else? If you're simply saying, I think that my results are going to yield differently than the population's results, then all you're saying is a non-directional test, because it can either be on the positive end or the negative end. It can be better than something or worse than something. It can increase something or decrease something. So in reality, that's what we talk about in terms of having the tails, 1 or 2 tails. And if we're talking about a one sample Z test, for example, here we're saying that 100% of people are accounted for underneath this curve, underneath this distribution. So if 100% are accounted for, and we were talking a non-directional test, and we're saying an alpha level, the default of 0.05, we're essentially saying that between this 1.96, positive and negative, 95% of people fall between this space. So that would lead us to a 0.05 of an alpha level. But what if we wanted to make our test a little bit more strict, harder? We wanted to make our test something where it would be harder for you to find a significant difference, because getting a Z test or a Z score that was larger than 1.96 leaves you a 2.5% here and a 2.5% margin of error here. So what if we wanted to make it stricter? You only have a 1% chance or a 0.01% chance, like a 1%, a penny chance of being there. Then you would change essentially your alpha level. So if you would change the alpha level and say, for example, you want a 0.01 chance. So you want a 0.01. You have to go to the unit normal table and find out what number, what Z statistic gives you a less than 0.5% chance here and a 0.5% chance here. Because if we're saying 0.01, we're saying 99% is in the body. 99% of everyone else's results will be just like yours, just like the population. You only have less than a 0.5% chance on either side to be significantly different. And if we were looking at it, we'd go look at that particular Z score in the back of that unit normal table, and we would come to the value of 2.58, positive or negative. And if we want to get even stricter, which are the 3 most common that are usually used, we could actually go to 0.001. In other words, we're like 99% accurate. If we're going there, we're going all the way to a Z statistic of 3.0 0.30 on the negative or positive end. So imagine actually getting a z-score that's bigger than 3.30. It's so hard to get. Why? Because you have a less than a half a percent chance of even getting there, because we're 99.9%, or 99, or 95% accurate. So you're really talking about your level of accuracy. So your margin of error, right? Or in other words, the idea of you being significantly different than the norm, right, is really difficult. You're making your test more strict. This is a two-tailed. But what if you decided, you know what, I don't believe there's a difference somewhere. I know exactly where that difference is. So imagine you were saying, I think it's better. I think it increases. You're talking about something going into a high end. In other words, on the positive side of this distribution. You're believing that your results will yield an increase, a better, a higher. You would jump to the one-tailed test. If you're going to the one-tailed test, these numbers now change, because these numbers are giving you the percentage split by 2. In other words, 5% split by 2 gives you 2.5% here and 2.5% here. But what happens when the entire 5% is now on one side? So then you'd have to go look up a different statistic. And in the unit normal table, you would find out if this number is now going to change. This number would now change to 1.65, right? And this would give you the entire 5% on one side. The number would also change to 2.33, and it would then change to 3.08. Using the same alpha levels of 0.05, 0.01, or 0.001. But that means that the entire percentage, the 5%, the 1%, the less than 1%, are all particularly on one side. And because it's symmetrical, it would be the same on the other side if you were simply saying that it was worse, a decrease, something that lowered something, right? You were talking about the direction of being on the negative end. You would use these same numbers, but just on the negative side. That's what we refer to when we talk about a one-tailed and a two-tailed test. And then if you think about it, this actually talks about how strong or how strict you could have your test. And remember I told you, there's 3 different people or 3 different entities that choose these particular numbers that you're going to use. 95% accuracy, 97, 98, 99% accuracy. There's 3 different entities. Whether it's yourself who has the power, the researcher, in other words, the funder for the researcher, the one who's paying for it, or the actual company or field of research, because you want to do the same thing as everyone else is doing in terms of level of strictness and difficulty. You don't want to make yours easier, because then no one actually believes you. If someone's out there testing at 95% level of accuracy and then decide to now do 97% and everyone shifts to 97 and you stay at 95, your results wouldn't be accurate because you're not as strict as them. Your test wasn't as hard to reach a result as they were. You were more lenient. That's a problem. So if we're talking about that, that means that the alpha level, this particular number, and that choice that you're doing, your statistical significance number, can lead to type 1 errors. Type 1 error has to do with the fact that, did you have a false positive? Type 1 error can lead to a false positive. So what do we mean by a false positive? Well, if everyone is running testing at 97% and you're running it at 95% and you landed at the 96, in other words, 97 puts you right here and you landed right there because you decided that your cutoff point was going to be here. So your cutoff point was more into the body. So if you decide essentially that your cutoff point was 1.96 and everyone decided that their cutoff point was 2.58 and you landed beyond your critical, it doesn't make a difference because everyone else's critical began at 258. So in other words, a false positive is the idea that you made your test too simple and you landed in the tail. But if you would have made it more strict, further out into the tail and chosen a different alpha level, then you probably wouldn't have yielded the same result. You probably wouldn't have found a significant difference between your sample and the rest of the population. So that's very easy to find out. You can basically do a retest. And a type 1 error, just run the test again with a different sample and see if you yield the same result. And you could figure out if you had a type 1 error or not, a false positive. But what happens when you have a type 2 error? A type 2 error isn't as easy to figure out. A type 2 error, right, is actually called beta. A type 2 error, we use it as a beta, in other words, that B, right, that Greek-looking B. It's because the mistake can be anywhere. It could be human error, you typed it in, it could be one of the sample size, people lied, it doesn't matter. What it basically means is that it has nothing to do with how strict or the design of your test. It has to do with everything else that could have gone wrong, which many of the times could be simply human error, that could have gone wrong. So type 1 error is very easy to find out if you made that mistake, because the retest and the retest again and again, if you're yielding all these results that show significantly different samples, you can be sure of the fact that your program is actually going to lead to a different result. But if only one of them gave you a significant in the actual significant area and everything else gave you in the body, which means the area that says HO, you're just like everyone else. If only one of those tests that you ran landed here and everything else was in the null hypothesis zone, then in reality you realize that one sample happened to just be a fluke. But what happens when the mistake is anywhere else? You have no idea. So we call it a type 2 error. A type 2 error is simply where there's a mistake, where you really don't know where the mistake is. And just like this is a false positive, this is a false negative. So you ran a test, let's say, to cure cancer. And in the end, your results said, you didn't cure cancer. Let's face it, most people haven't cured cancer. So then in reality, what did we realize? Okay, this didn't work out. Let's go back to drawing board and try again. But if you would have cured cancer when everyone else hasn't, someone will challenge you very quickly. So the retest will tell you if you made a mistake. But here, you didn't cure cancer just like everyone else, so why would you think that you actually cured it? You would just assume, nope, this program, this treatment, this medication didn't work, and you'd move on and try another. And that's the problem with the type 2 error, that you wouldn't know that you actually had a false negative. In other words, you wouldn't know that you actually cured cancer, but because there was a mistake inside of your design somewhere, you actually came out to the answer of you didn't cure cancer. So that's the easiest way to pretty much understand these type 1 and type 2 errors in terms of understanding the alpha level. Now, once you actually go and get over these type 1 and type 2 errors, you also have to start thinking about something further. Besides the alpha level, you also want to make your test stronger. In other words, more powerful. And you also want to be able to test, not just in the power, the magnitude. In other words, the strength. How strong was the result? And those are two different things we're going to talk about in the next video.